Good afternoon, students. In DTSP FIR filters unit 3, the well-known method of designing FIR filters are as follows, that is Fourier series method, window method, frequency sampling method and optimum filter design method. Okay. So now we see about step to design FIR filter using Fourier series method. If HD of e power j omega equal to 1, 0 less than or equal to omega less than or equal to omega c. 0 means otherwise is a given specification. Step 1, draw the graph for given specification. So we have a LPF, HPF, BSF and DPF. Okay, likewise we have a diagram. LPF diagram, then for the HPF, then we have a BPF, band pass filter, then band stop filter. Likewise we have idea. This is the first one. First of all, we have to find out the width filter. Then step 2, find alpha. Alpha is equal to n minus 1 by 2. Then find HD of n. Desired impulse response. That is HD of n equal to 1 by 25 minus pi 25 HD of e power j omega into j omega into d omega. Filter coefficient HD of n for different type of filters. That is in case of HPF or HPF or LPF or BPF, BSF means based upon the filtering section, the response filters are varied. So, like this we have the formula. Okay, these are all the formulas. Then find H of n means H of n normal impulse response, not in the desired. Then H of n equal to HD of n for minus infinity less than or equal to n less than or equal to infinity, 0 otherwise. And then fifth step we have to go for the H of z transfer function. H of z equal to summation n equal to 0 to n minus 1 by 2, H of n z power minus 1 plus z power n plus H of alpha if alpha equal to 0. Otherwise, alpha not equal to 0 means formula will be changed. Find the transfer function of the realizable filter H of z equal to z to the power of minus n minus 1 by 2 into H of z. Then find magnitude of H of z. Now we see one problem, that is design a FIR LPF with cutoff frequency of 1 kHz and sampling frequency of 4 kHz with 11 samples using Fourier series method. Given F equal to 1 kHz, that is from the sum, Fs equal to 4 kHz, that is the sampling frequency, the number of samples n equal to 11. Omega c equal to omega c into t, that is omega c by Fs. So we have to calculate it 2 pi 1 into 10 to the power of 3 whole divided by 4 into 10 to the power of 3, Fs is available. Then finally 5 by 2, that is 0.5 radian per seconds. Then desired frequency response is HD of e power j omega for low pass filter. So here we have a LPF now from the sum, so that's why we go for the low pass filter. HD of e power j omega equal to 1 for minus omega less than or equal to omega less than or equal to plus omega c, otherwise 0. We have a limit. Then the desired impulse response HD of n from the formula we can get it, HD of n equal to 1 by 25 root of minus pi to 5 HD of e power j omega into e power j omega into d omega. So limit we have to apply it minus omega c to plus omega c e power j omega into d omega. So we have to integrate the two term. Finally we get the result HD of n equal to 1 by pi n e power j omega c n minus e power j omega c n by 2j. So then sin omega c it converted to sin. So 1 by pi n into sin omega c by n. Then we calculate the H of n, impulse response H of n of FIR filter. Okay. So at a time we have to calculate HD of n equal to sin omega c n divided by phi n, already we know. So in case n equal to 0, so we have to apply the two condition, n equal to minus n minus 1 by 2 to n minus 1 by 2, otherwise for n equal to 0 means omega c by phi. So already we know alpha minus 1 by 2, no? So 11 minus 1 by 2 equal to 5. Now we calculate n equal to minus 5 to plus 5. N equal to 0 means w omega c divided by pi na, that is equal to 0.5. When consider n equal to 1, we have to apply it, whatever we have the n value at a time we have to apply it and get the result. So likewise H of 1, H of 2, H of 3, 4, 5 we have to calculate it. Symmetric condition is also followed, no? So at a time n equal to minus 1 means H of minus 1 equal to H of n. N equal to minus 2 means H of minus 2 equal to H. So symmetric. So minus and plus also have the same value. So we have to apply it. So finally we go for the transfer function. H of z equal to z power minus n minus 1 by 2 into z into H of n. Okay. So if you apply the H of n elaborate time means we get the result. Okay, the symmetric condition here followed, H of n equal to H of minus 1. So that value is repeatedly same. Okay. So, h of z equal to h of 0 z power minus 5 plus h of 1 z power minus 4 plus z power, because symmetric, no. So, that is why z power minus 3 plus z power minus 7. So, likewise we get it. So, finally, we have to apply it that value, then we get the final result. Okay. So, this is the final structure of the FIR LPF. Then we go for the magnitude function of h of z. So, separate formula is available. H of 0 plus summation n equal to minus 1 n minus 1 by 2 2 h of n into cos omega n. Then it is the elaborate the summation value, then we have to write the function. Okay. Thank you.